All right, homework from five. Actually, I think this is page 512 now. Actually, I just my last homework one was about this one. We get some room on the same page, so I'll stick with this. Okay, so we have two balls of string. One has this sort of dimensions, 3 centimeter radius, costs $1. This one has a 6 centimeter radius and costs $6.50. Now you could do this in the similarity way. You could say, well, since these lengths are doubled, the volume should go up times 8. So the cost should be a measure of volume. And $1 times 8 would be $8. This is the better deal because it's less than $8. Or you could say, okay, let's actually find this volume. Let's get a cost per cubic centimeter on the money and see which one has a cheaper cost per cubic centimeter. So that's maybe a little safer. Okay, so the volume of this one is 4/3 pi r cubed. The volume on this one is 4/3 pi r cubed, which is, yeah, I really don't want to do this. I want to just do the similarity thing and say, yeah, it should be $8. Okay. 4 pi r cubed, 3 cubed divided by 3 is 3 squared. 9 times 4 is 36. This one I get 6 cubed, which is 216 divided by 3 is not easy. Okay. 216. That's 3 cubed, by the way. Or 6 cubed divided by 3. I couldn't do that in my head. Nope. Times 4, because I'm about 4/3. 288. Okay. Okay, and we can cut. And you know what? I bet you, just to make me feel better, if I took that divided by 8, I should get 36. Yeah, because it's 8 times bigger. But that's not the way we're doing this. So if I want price per cubic price per cubic centimeter, I need to put, that's how I need to do my fraction. This is $1 for 36 pi cubic centimeter, so I'm paying that much per cubic centimeter. Here it's $6.50 for 288 pi cubic centimeters. Yeah, again, the method of similarity where you go, it should be 8 times as much because it's 8 times as much volume. I think it's way easier. 1 divided by 36 pi is really easy to mess up. So each cubic centimeter on that one, see, and it's this tiny little decimal. The other one is 650 divided by 288 pi cubic centimeters. And that one turns out to be, having my pi. There we go. This one is cheaper. This one's like 0.8 cents per cubic centimeter. This was 0.7 cents. So 0.008, 0.007. I'll just do that. $0.008 per cubic centimeter. And this one's 0.007. So any way you do it, that's the better deal. All right. All right, we have a sort of a hollow ball where the radius of the outside is 11 and the inside is 10. So we have to find the volume of, the rubber in between, which would be big. That's really not a very helpful picture. Volume of big minus the volume of the hole, basically. Okay, so this is 4/3 pi r cubed minus 4/3. By the way, I went to another page. I'm on 501 now. Pi r cubed. This one's easy. This is 10,000 times 4. So that's 1,000 times 4. Times pi and divided by 3. This one is not as easy. That's 13. Yeah, I got to multiply that by 4. 11 cubed is 1331. I can say that faster than I can. What is not? Faster I can type it. Yeah. The times 4 divided by 3 is what's weird. Okay, so this is 5324 pi over 3. So what I have is this many pi's over 3. Does that divide by 3 nicely? It'd be really nice if it did. I don't think it does. Yeah, 1324 pi over 3. Do they want that approximately? Nearest cubic centimeter. Yeah, they do want that. 1324 over 3, which I have, and then times pi. It doesn't like to click right there, does it? 1386.5, I'll say. in part B, they're giving you a formula for the volume of the rubber. You could also say, well, let's take this whole thing, cut it apart, spread it out, lie it flat, which I can't really draw because there's no way to flatten out a sphere. But if you can imagine that, the inner surface area being the base of some sort of wacky prism where that's the inner surface area is the base and this sort of thickness is the height. The surface area of the inner, it only has two ends, times thickness, I'll call that T. It's supposed to be the volume of rubber. So what I have here would be 4 pi r squared, and that's the inner radius, good, because that's 10, that's easier to deal with, times the thickness of the rubber. Well, the rubber is 1 thick, so that's not hard at all. That's 400 pi cubic centimeters. That's all we're supposed to know. We're supposed to compare this with this. Okay, let's see what that's like. All right, 400 pi. Well, it's 441 pi, so it's going to be less. 1256. That's quite a bit less. 1256.6. So you're supposed to look at how these compare, and 1256 is way too small. So what's going on there? Well, if you think about it, if this thing is, it's not flat, it's a little curvy, the inner surface of the sphere, there's going to be some difference between thinking of that as the basis of some bizarre prism and calling this the height of the prism, than actually taking sphere by sphere. This should be a lot more exact than this kind of approximation thing. Part C says, is the approximation in part B better for a ball with a thick layer or a thin layer? Well, I think you could probably surmise that this is kind of a weird way to do it. Would be to take, flattened surface area of the middle times the height. We're probably going to get better results if that isn't such a stretch or such a curve or such a bend of this one. So I'm going to say thinner. That's kind of an intuitive, philosophical almost kind of argument about why thinner is better on that one. You're altogether going to have smaller numbers, which I guess maybe would hint at the fact that they would be farther apart, or sorry, closer together if they were just altogether smaller. But other than that, I have no scientific reason why it should be thinner, other than just this imagination piece of flattening this thing is going to skew the result a little bit. If this is thinner, then these things will be closer together, and so that approximation isn't so wacky. That's all about all I can say on that. Okay, in 29 you have a circle of radius 9, and you're going to spin it around, or sorry, radius diameter of 9, and you're going to, it's like you could hold it here and here, and you're going to spin that thing. It's like when you're flicking a coin on a table, like you hold it here and you flick here, and it starts to spin this way. It's going to spin out, and it kind of looks like, actually, as it's spinning really fast, kind of looks like a little ball of coin there. It's going to look like a sphere like this. It's spinning around this diameter, which is just twisting on its axis. All right, so they're saying, what's the surface area and the volume of that thing? Well, it's a sphere of radius 4.5, so all we got to do is apply our surface area and volume. Surface area is 4 pi r squared. Which is, I'll do volume later, just don't want to forget it. 4.5 squared is not pretty. It's 20 and a quarter times 4. Oh, that'll be pretty, because I got a quarter there. So times 4 is 81. And volume is 4/3 pi, yeah, 4.5 cubed is really not pretty. Whoops, I was saying cubed, I wrote 3. 4.5 cubed. 4.5 to the third times 4 divided by 3. Hello? Can you hear me clicking out there, geometry? I'm not. See, the calculator I gotta deal with. 121.5. That's fine. You can do it like that. Or I could make that a fraction and call that 243 over 2 pi. That's fine. Either way. Alright, back to page 512. Number 16 is about this construction column. And yeah, trying to make something stand up stronger is not about making the thing similar to this and making it basically taller all the time. It's about the cross-section of area. So it's about making it thicker, basically. The thicker it's going to get, the more it's going to be able to hold up. So they're telling you that this one is 3 times as high as this, and then every other way similar. So we were talking about similar figures, so that's one of those deals where I am talking about a K situation. The larger column is how many times as strong as the smaller column. Well, that's a measurement of area. So I should use K squared for that, which would be 9. Part B is asking the larger column is blank times as heavy. Well, heavy is a measure of weight, which is like saying we're talking about the volume of that thing, which is K cubed. Then here's the hard part. Per pound of material, which one's going to be able to support more weight? Like, how much work is 1 pound of this doing versus 1 pound of this? Well, this thing is this thing supports 9 times the weight that this one does, but it takes 27 times the material to build it. So we've kind of lost a lot of the efficiency of this column. We went and made it 3 times bigger in every direction. Yeah, so I think that's the best way to answer that. You could do some crazy division stuff and say, like, make up a weight this is supporting and make up a weight this is supporting and how much this thing might weigh and how much this thing might weigh. But I think the argument of just, okay, this thing got, when I tripled everything, this thing got 9 times as stronger, but it got 27 times heavier, that's not as efficient as it used to be. So the question, the way it's worded is, which can support more per pound of material, the smaller or the larger? It's going to be the smaller one. Another one of those philosophical questions I may or may not ask. I'm not going to tell you. Okay. All right, number 17 is a classic, like Phineas and Ferb level similarity question. These are supposed to be similar figures. I know that the lateral area of this is 8 and the lateral area of this is 18. If I was to compare those big to small, I would be finding the ratio of areas. So that is K squared. What I need to do with this 32 then, since I need to make a new volume of it, I need to multiply it by K cubed. So I have K squared. That's actually 9/4 if you reduce that fraction. No, it's not 9/4. Oh yeah, it is 9/4. Just reducing the fraction. Yeah, divide both those things by 2. That means that K is the square root of that. Yes, I'm going to need K in order to figure out what K cubed is. And notice how they give these really nice numbers that actually have whole number square roots. That means K cubed, which is what I want to actually operate with, is 27/8. So I have to find 27/8 of 32. 32 times 27/8 is like 4 times 27, which I don't want to do in my head. Thing turned off again. It's a little over 100, right? 108. So this volume is 108. Remember, it's 9/4 times the area, so it has to be 27/8 times the volume, because all the heights and all the lengths on there are 3/2 as big on this one over here. All right, last one on page 502. This one looks kind of crazy because you don't really know what you're looking at here with the radius of that cylinder. The thing is, it says it's a cylinder with height 12 is inscribed in a sphere, meaning these circular edges both touch the sphere completely, with radius 10. Find the volume of the cylinder. Okay, volume of a cylinder is simply area of its base times its height. Well, the height is no problem. But what on earth is the area of this circle here? Well, for the area of that circle, it's going to be pi, you know what, let me call it x because I have another, well, no, I'll call it r. Fine, because I know the radius of the sphere is 10. It's pi r squared times 12. I just need to know what r is. Well, r is in a right triangle like so. From the center of the circle to this point on the sphere, well, that's 10. That's nice. R, I don't know. What is this height here? Well, if this is the center of the sphere, it's also halfway between these two identical circles in the as the bases of the cylinder. Those circles, if they are identical, which they have to be if it's a cylinder, are pushed out away from the center of the sphere the same amount. So that would have to be 6 up and 6 down. So doing that with Pythagorean theorem, I find out that r would have to be 8 in that little triangle, 6, 8, 10. So then I'm ready to go. Pi times 64 times 12, which is 768 pi. Very good. Okay, that's it for 502. That's it for this video. I'll go back to making more test review ones. See you in a minute.